My name is Lloyd Palm. I'm the CTO at Phenomics. Phenomics is an analytics company that helps commercial trucking fleets make more money by optimizing their fuel economy. And so we offer a software as a service that has a bunch of analytics that are geared towards and targeted at that activity. Just out of curiosity, before we get started, did anyone have a chance to look at the presentation from Strata in San Jose from March? Because it was kind of a prequel to this at a high level, the business value part of it. Anybody? That's okay. We'll sort of reacquaint ourselves with what we were going through in that previous presentation so we could use it as a precursor here. Also, to what extent do folks have familiarity with the term digital twin? Is that a familiar thing or no? Okay, so that's good too, because hopefully by the end of this, we'll, next time when the question is asked, you'll say, oh yeah, I know all about these things. And then in terms of machine learning familiarity, who has run a machine learning workflow and maybe even in particular TensorFlow, Google Cloud ML? Okay, good, one person. So when I get stuck, you can help me answer questions. This is gonna be good. All right, so let's get to it and we'll see. So this is the guy that we're working for, or more importantly, this is the guy that the digital twin or twins that we're gonna build are working for. You've heard actually, if you've gone through a number of presentations at this conference, it's always very important to begin with the end in mind. And so this is the person that we're essentially gonna answer questions for and provide predictive information that makes their life easier and ultimately makes their fleet more profitable. So key questions for this guy. You know, are their trucks or are his trucks fuel efficient? And so that's actually, as it turns out, and we'll come to see as we go through this, not an easy question to answer. It's not as simple as looking at the sticker on the window when he purchased the truck and saying, okay, I'm supposed to get this many miles per gallon. It's quite a bit more complicated, and that really won't do it when he wants to answer this question. The other thing that's on his mind on a day in and day out basis is, do I have the most fuel efficient trucks given the operation that I have? So given the routes that I'm traveling and the freight that I'm delivering, do I have the right truck for the job? And so that's another key question, also not very easy to answer for fleets that have many trucks and lots of activities going on. And perhaps maybe the holy grail of questions that they would ask and need to have answered is, if I have a piece of freight that I have to deliver from point A to point B, how much is that going to cost in fuel dollars? And that too is often very difficult to answer ahead of time. And it can have a lot of impact on the business if you can provide that information with a decent level of accuracy to sort of drive the pricing and flow of understanding of cost within the business. So keep these in mind, because as we're going into the technical details, these are the reasons or the target, if you will, for the digital twin technology. So let's go through what we're going to cover today quickly. First thing I want to do, and this is the part where I'm going to reacquaint you with the previous presentation that we did in San Jose, but you have to have a little bit of appreciation of exactly how important fuel economy is to these fleets. It's a huge driver, big impact kind of item, and so we'll go through that real quickly. The next question that you would probably ask is, okay, I got it, fuel efficiency is important, but how can a digital twin help? And maybe to some extent, what is this digital twin thing and why is it going to make a difference? So we'll help in that respect. And then, okay, we'll get a handle on a digital twin, but then we have to really focus on what is it that we're going to optimize to help answer some of those questions that we just went through for our fleet manager. And we'll quickly go through that. Then we'll step into how to build this digital twin, the thrust of the talk. We'll get into how to go from sensors to features, features being what we need to drive and work with from a modeling perspective to predict outcomes. We'll choose different modeling techniques, and in fact, we'll go with a baseline technique here in this presentation, which gives us a real cheap and dirty, simple approach to doing what we're going to do from a predictive standpoint, and then we're going to graduate into using something more complex, more sophisticated. And then how do we deploy these things? So there's going to be this contrast between an offline process where we're building up a model and we're making sure that what we have is worthy of using in production and answering those questions that the fleet manager has day in and day out, to graduating into, okay, now we've got that model in production, how do we make sure that it continues to work effectively, and also how do we replace it with a better model as we continue to work through it in the future. And then towards the end of the presentation, we've got a handle on how we got a model in place and what was the way in which we do that. But then we want to use the digital twin. We have to come full circle in many cases here, where we're going to go back to those questions and really drill into how the model and this digital twin is helping us answer those questions. That'll, in particular, the ones we'll look at today are tracking fuel economy for every single trip that the fleet is running. And the other one is benchmarking the truck classes that they have within their fleet versus all the different specific trips that they run within a period of time. And then I'll finish up with, hopefully, is a consolidated or condensed summary of what you might consider to take away from all this. So let's get into it. So fuel expense in commercial trucking is a big deal. You hear people use the anecdote that everything around us, including everything in this room, was on a truck at one point in time. That's how it got here. And so there in the United States is a truck for every 100 people, roughly. So there's a lot of trucks out there. We sort of start to take them for granted, given they're all over the place and around us all the time. But the thing to key in on is that there's a fair amount of money flowing through those trucks on a day in and day out basis. Billions of dollars of fuel is spent every year in the United States on moving things around using these big Class 8 tractor trailers. And by the way, what we're going to talk about today from a modeling and a digital twin perspective is fuel economy in particular, and these Class 8 trucks in particular, the big ones. Nothing about what we're talking about couldn't be applied to different kinds of trucks or cars, for that matter, or even things other than fuel economy, but we'll keep it on that theme to try to make it more focused and hopefully more understandable. But big deal, big optimization problem here, lots of fuel flowing through all these trucks. So that's in the aggregate, that's the macro sense, but what does the expense of one specific truck look like? And in particular, it costs about $130,000 a year to run one of these trucks. And that expense, to a large extent, is driven by two particular things. The person who's driving it, the blue category here in this wheel, and the red part, which is what we're going to focus on today. It's the fuel that is necessary to move that truck. So those two things essentially become the lion's share of the cost for every single one of those trucks that are part of that macro view that we just went through in the previous slide. And so the digital twin that we're going to talk about today is focused specifically on this red segment, the fuel expense of this truck, and those questions, of course, that fleet manager has. The reason those questions are so important is because this piece of the pie is so significant from a cost perspective, day in and day out for that trucking fleet. So what is a digital twin? Digital twin and model can be used synonymously. A digital twin could encompass as little as one specific thing, as we're going to talk about it today, fuel economy or gallons per minute fuel use for a specific truck on a specific trip. But the thing to note is what we're setting up here is we have an actual physical asset within the fleet, this blue Kenworth T680 truck. It has a vehicle identification number that we're all familiar with from our own automobiles. It is a specific physical thing. And every day, that specific physical thing goes out in the world and runs routes, as annotated on this map, a specific set of trips or trip. And it consumes fuel. It consumes an actual amount of fuel. And what we're going to do is we're going to have a digital twin, a model, that mirrors exactly what that specific physical asset is doing with respect to fuel consumption. So every single trip that we go through with this truck, we can also ask the digital twin to say, hey, this truck just used 20 gallons of fuel to go from point A to point B. What do you think it should have taken to go from point A to point B? And the digital twin is constantly used to compare what's actually being burned in this physical asset, this specific truck, and what it predicts should have been burned given the characteristics of the trip that it just ran, so that we can constantly monitor and watch what's happening with that fuel expense, which we've already discussed is really important. So we want to keep a strict eye on it and track it day in and day out. So I have a physical truck, and I also have a model, a representation of that truck in software and in a machine learning model that sits there dutifully day in and day out and tracks what that truck is doing. Make sense so far? That's what we're about to do. Okay, quick question.
So when you say predictive performance, are you talking about its predictive performance for that particular truck based on that particular truck's past history? Maybe taking as a prior in general, the camera, whatever, but tracking that particular bin and updating that in some way? Or are you saying that there is some sort of instructing what this truck should get if it's running correctly?
So it's actually a little bit of both, and I think some of it will come out. So let me go through it, and if we don't adequately, or I don't adequately answer the question, we'll go back to it at the end and really drill into it. But the answer to both those questions is yes, and so hopefully we'll see exactly what's going on as we go through this. So you're probably wondering, okay, given that we want to predict what the fuel use of that truck was at any given moment in time or with any trip that it's run, what drives fuel economy? And so it really breaks down into the two different sides of the equation. One of them is completely driven by the behavior of the driver of the truck. And actually, this is a huge swinger. The driver can have 20, 30% impact on how much fuel is actually burned by one of these trucks. And everybody's probably even had personal experience with this in terms of how you drive your own car. If you drive it aggressively, you tend to use more fuel. If you drive it more conservatively and sort of smoothly as a descriptor for what would be good fuel economy driving, you use less fuel. And so driving behavior is a big deal in terms of what's going to drive how much fuel was used on a particular trip. So setting that aside for a second, then all the other aspects of the truck, the truck configuration, of course, is at play here. Its make, its model, its year, its engine, its drivetrain configuration, all of the things that make it that specific kind of truck and drive how much fuel it uses within a particular operating scenario. Of course, the route, hills, mountains, flat, hot, cold, these are all things that determine how much it's going to use. And then the load itself, how heavy a load am I carrying? Is it only half full? Perhaps it's not pulling anything at all at this moment because it's going to pick something up and it doesn't have a load. So that certainly drives it to a good extent. And then the environment, as I mentioned, hot, cold, windy, rainy, snowy, those things all factor into this. So at the highest level, we sort of have to appreciate that there's so many different dimensions that are driving the fuel economy. What we want to do at this point is go and manufacture features or data items that align with each one of these things so that we can capture all the context that we need in order to predict the fuel economy of that truck, trip in and trip out. I want to dive inside the engine of the truck for a second. So this is from a particular Freightliner Cascadia truck. It's kind of a busy looking picture, but I'll sort of walk you through it. You'll get a sense of what's happening. So along the base or the bottom of this, the X and Y dimensions are speed and RPM. And so the Y dimension is how fast the truck is traveling along the road. So 60 miles an hour, 100 kilometers an hour, that sort of thing. And then the RPM is how fast the engine is spinning, 1,000 RPM, 1,600 RPM, that sort of thing. And then the Z-axis is the amount of power the engine is putting out, how much torque the engine is driving at any given moment. So in this picture, the colors of those samples that we're taking as this truck is being used are indicative of the fuel rate that's flowing through the engine. So if you see yellow or hotter colors, that's high fuel use. And if you see cooler purple colors, that's lower fuel use. And so the rule here that comes out when you look at this picture is in the engine, the faster I spin it, or the more power I demand from that engine, the more fuel it's going to use. So from a data science, and I'm looking for variables that are correlated to fuel use, this picture tells a 1,000 words kind of explanation. I'm looking for high power output, high turns, revolutions of the engine, and that's going to dictate higher fuel use. And so those variables are going to become very important as we look at what do we capture, what's the context of these trips that we're running with the truck that are then going to translate into our ability to predict fuel use within the models and the digital twins that we're going to apply to the problem. So things to take away at this moment, now we've sort of looked at inside this very low level detail of what's happening. The target variable for our model, for our digital twin that we're going to predict around is the gallons per minute fuel use of that truck during a trip. And so it's the color within this graph. And the faster that engine spins and the more torque or power we demand from it, that's going to dictate more fuel use. And so if you take that away from this slide, you're now an expert in terms of diesel engines and what's going to drive fuel economy. Oops, sorry, wrong direction. So let's go through the modeling process. So essentially we walked through at this point, why is this so important? What are some of the things that are driving fuel economy? Why do I want to look at specific variables or context around the trip that are going to ultimately be able to act as features that I'm going to use to model this and predict fuel economy? Very, very similar. So full physics simulation model, instead of using a machine learning technique, we would essentially use closed-end physics-oriented equations, differential equations, solving multiple equations at the same time in order to physically model the asset. That could be a different technique than what we're talking about today. The end result is similar. Like in other words, what I'm trying to do is I'm still building a digital twin model. I'm just doing it with physics-based simulation. This is sort of take the approach where understand what drives fuel economy and then use a traditional machine learning workflow to come up with a mapping of the distribution of all the things that drive fuel economy to actually what you're going to predict is going to happen from a fuel economy perspective. The end goal is the same. The way in which you're going about it is a little different. Yeah. Yep.
This could be an important tool that you can arrive at certain different conclusions, the value result in scarcity, and you enrich with this model.
Yep, absolutely. This is actually, you bring up a very interesting idea. We'll see in a second during the modeling process, we're going to make a really simple model very quickly, and it's going to drop a baseline of performance for our predictions of fuel economy. And if you have a physics-based model, that would be a great way to put that baseline and use that for the baseline, because then any machine learning technique, full of its sound and fury and complexity and all the different things that we can do with it, it should be able to beat that physics-based model, or else what good is it, right? Like if I already have the physics-based model and I'm using it, there's really no sense in going after the machine learning technique unless it's somehow going to benefit in terms of better predictions, more accuracy. And so you'll keep that in mind because we'll see it come out as we go through this. So the modeling process that we're going to use is thing to point out here is that this is an iterative offline process. So in other words, we either don't have a model in place yet that we're using to predict fuel economy, or we do and we're working on the next one or a better one. And so this process that I'm about to describe from a modeling perspective is offline and is not currently being used. We're evaluating how to get the next model in place that is going to be used. Feature generation or pre-processing is going to occur in an analytic pipeline, and so we'll quickly go through an illustration of what that pipeline looks like. we're gonna put together a sample of a lot of trips in order to use as a corpus for the development of our model, and we're gonna break those trips into 3 distinct groups, again, consistent with a traditional machine learning workflow. We're gonna end up with a training, a validation, and a test set that's coming from all these features. Our evaluation metric, as I pointed out in the earlier graph, remember our target variable is the gallons per minute fuel economy. And so from a loss function perspective is we're trying to minimize the error between the actual fuel use of the truck and the predicted fuel use that the digital twin is going to give us. And if we subtract the predicted from the actual, we end up with an error, and we're going to try to minimize the root mean squared error of that. And so that's what we're optimizing. And we're going to generate this performance baseline that we just talked about. In this case, we're going to point a simple linear model at it. If you had a physics-based simulation that was the current baseline, if you will, you could use that instead. And then we're going to iterate the model. We're going to, as everybody realizes from a traditional machine learning workflow perspective, there's a lot of knobs and levers to pull in order to make this model work effectively, and you don't know ahead of time exactly what way in which to configure it. So there's an iterative process and sort of some intuition that you use to figure out what set of parameters are going to work best. And so we'll talk about that just briefly. And then you know, the final step, if you will, in this model process is to test how it does on data that it's never seen before. Does it generalize when you put it in the wild and start feeding it trips that it hasn't seen? How close does it actually come to performing like the actual asset itself? And so this is a really important thing. You see a lot of things out on the web and in different machine learning blogs. If people don't do a good job with their test data set and assessing their models, you end up putting something in production that sort of lets you down from a performance perspective. It sort of leaks you know, information into the process of building the model unless you do this effectively, and you end up producing a suboptimal model. So here's the system context for the feature generation pipeline. So the thing to point out is every single time one of these trucks runs a route, from the time the key is turned on till the time the key is turned off, we need to capture a set of heuristics about that trip, which we're going to use, or the digital twin is going to use, to make a prediction about how much fuel should have been used for that trip. And so if you start off on the side over here with the truck and the truck sensors, there's a flow of information that comes off all of these modern trucks. You plug into sort of a multi-drop bus, a network, and there's compute capability on the trucks that is consuming all of that sensor information as it's being produced in real time, and generating a set of metrics that are being streamed to the cloud, cellular and or Wi-Fi, depending on the connectivity of the truck at the given time. And every single trip, we sort of capture a set of raw information that makes its way up into the cloud and is captured in a time series database. And that is the context of the trip that was just run that we're going to use to drive the digital twin and its prediction capability. Remember I mentioned earlier that the driver is a big swinger to fuel economy. Phenomics actually has a completely separate model. Actually, we have a family of them, and you sort of see some of them here, that isolates what the driver's effect was on the fuel economy for a specific trip. So in essence, we're able to subtract off the effect of the driver so that we can really zero in on the truck and see what the truck's characteristics were for that particular trip. So the top part of that pipeline after we get to the cloud is to isolate that and remove it from consideration. Then there's also a load weight model that basically predicts or generates a prediction for what the load was during that particular trip, because we don't have explicit knowledge about what it was pulling, but we generate a predicted value based on you know, watching the acceleration characteristics and things like that of the truck that allow us to predict the load weight. All of this ends up being processed into a set of features for the trip, which we're going to look at in a second, and stored within a data warehouse that essentially is a list of trips that are run by each of the individual trucks on the network. And so this gives you a quick tally of the kind of features that are in that data warehouse. Quick question? Yes, but not in the way you think. We don't have an instance of the model for every specific truck. There's embeddings within the model, one model, that represent the make, the model, the year, the specific drivetrain, and all those characteristics. So those embeddings essentially embody separating out the hyperspace that all these trucks are operating in, so that each and every one of them is represented, at least from the lowest level class of truck that it represents. The other thing that you'll see when we go to use the model is that we separately store the statistics that are being generated, the error that we talked about as being the evaluation for every single truck, because we're going to want to scrutinize every single truck in terms of how it's been performing historically. So stick with me. If I don't answer it completely, give a holler at the end and we'll dive into it deeper, but we should go through it. So this is the quick list of things that pipeline is producing that become the basis of what are the features, if you will, that we're going to use in our digital twin in order to do the modeling. So there's the gallons per minute fuel use for the trip. That's what we're trying to predict. That's the target. And then we have the make, the model, the year of the truck. That includes all of the aspects of its engine, drivetrain, things that we saw that determine fuel economy. Then we have average speed, average RPM, and average torque. Remember, we looked at that fuel map picture, and all those things are super important to how much fuel is being used. And then we start to pick up things having to do with the environment, like how many meters uphill, how many meters downhill, what was the temperature, and then the load weight in particular. So these are the variables and the types that cover the things that we looked at previously in the presentation that we talked about as driving fuel economy. We're mirroring the things that drive fuel economy and all these variables that the pipeline produces.
And what about the state of the tires?
Good question. I don't know to what extent that would have a big impact. I mean, certainly inflation of tires has an impact on fuel economy. So one interesting thing that you can do with a digital twin model is that you can do A/B testing. So in other words, you could look at how all the trucks that are the same make, model, and year, essentially they're all the same kind or class of truck. We could begin to isolate which ones have new tires and which ones have old tires, and accurately identify, quantify what's the effect of replacing tires sooner as it pertains to fuel economy. So hold on to that one too, because it's also a really good takeaway, is that when we get these digital twins in place, we put ourselves in a position to do exactly those sort of things. We can answer questions now that, you know, a lot of times before there was really no way to get a bearing on something like that. So if you're the tire salesman and you're coming into the fleet, you would want, or the fleet would want to know, hey, what's the economic benefit for me to replace tires early, or do I want to push them right to the legal limit of wear and that sort of thing? What's the benefit of me buying a tire inflation system so that my tires are always optimally inflated? How much does that really impact my fuel economy? And when I say my fuel economy, I mean that fleet's fuel economy, because these digital twins are keyed into their operations and their trucks. So it's not some conjecture about what's going to happen. It is what is happening. And so that's really a key thing about a digital twin. Once you have them within your fleet, what you're able to do. So here's the process. We take these trip records that we just talked about. Pipelines making these things, they're ending up in data warehouse, and then we pre-process them where we're going to go through some normalization of the data, and we're going to sample them, and we're going to break them into this corpus of training, validation, and test set. Again, if you're familiar with traditional machine learning workflow, this is what we're doing. It's the front end of this flow. And then what I want to represent here with the other little boxes in almost equation on this particular slide is you got to keep in mind that every time a trip is run with one of these trucks, we're going to compare how much fuel was actually used versus what the model predicted it was going to be used, and that creates an error, a difference between the two, and that error ends up creating what's tantamount to a Gaussian distribution of error, depending on what model we're using. And then, of course, everybody's perhaps familiar with bias and variance from a concept perspective, but if my model was perfect, there would be no error, there'd be zero error on every single trip. I'd predict exactly what was going to be used. I'd be smack dab in the middle of that bullseye, and everything would be concentrated right in the bullseye. If I have high variance, it sort of spreads out all over, meaning my error is sort of centered around the bullseye, but it's all over the place in terms of magnitude. And then bias shifts that error off to one direction or another. I may always predict more fuel is used than actual, or I may always predict less fuel, and that would be examples of bias. And so we're gonna look at those things because that's what's gonna give us a clue into how well our model is performing and whether one model is better than another. So I talked about a baseline. We talked about a physics-based model as maybe being a better baseline, but this is a cheap and dirty one. So on the y-axis here is the gallons per minute fuel use, and along the x-axis is the normalized speed of the trip, average speed of the trip. So not a lot of rocket science here, right? Like if I go to the right on the x-axis, I have higher speed trips. Higher speed trips use more fuel. I mean, you clearly see the linear relationship here where speed matters. You run the truck faster, you use more fuel. I mean, I think everybody intuitively can, see that that would be the case. The other thing that you notice here is that even though that is truly the case from a macro perspective, you can see that any given trip at a certain speed, there seems to be a wide variation in the amount of fuel that it uses. So there's a lot more going on here for sure. But if we look at a cheap and dirty linear model and we drop that regression line into this data set, I don't know, we get an R-squared value of, 70, 0.72, which is, yeah, there's good fit here, not great fit, but mediocre good fit. And as it turns out, the normalized root mean squared error, remember that's what we're optimizing here in terms of our function for the model, is around 8.5%. So what could I expect? If I use this cheap and dirty model for my digital twin predicting fuel economy, I'd get within, on average, 8.5% of what the actual use was. So not super accurate. But nonetheless, this is our baseline. We want to do this quickly. We want to make sure that we understand, okay, anything else that we do that's more sophisticated, it should beat this, blow it out of the water, or else it's probably not worth very much because the cheap and dirty simple way sort of set the tone or the baseline for what we're talking about. So far, so good? Makes sense? So this is the way to look at the error from that model that we were just looking at. Remember, I put the sort of condensed picture of what we're doing to assess the model. We feed it the test set, which it's never seen before, and we calculate the distribution of error for all those trips. So the test set may have tens of thousands of trips in it that have all those features that we talked about. And I calculate the error, meaning what did the model predict for fuel versus what was actually drawn during that trip. And we see this distribution of error. The green bar that I put there is just to show you that on average, this linear model is predicting high, meaning it's saying that the truck should use a lot more fuel than it actually is using. That's why we're sort of shifted to the left there. And it's also fairly wide from a variance perspective. It's sort of all over the map. And so you're starting to get a clue by looking at this distribution that linear model, it's our cheap and dirty simple one, is not very good, but nonetheless baseline of performance here. So let's throw something more sophisticated at it. So within the TensorFlow Google technology, machine learning platform and modeling, they have estimators that are sort of pre-baked into the library. One of them in particular is called a wide and deep regressor. We're doing regression here because we're predicting a continuous variable, that gallons per minute fuel economy. And so this wide and deep regressor is composed of two different modeling techniques. One of them is just a wide linear model. This is really good for capturing specific cases within the data that net certain fuel rate within our target variable. It essentially is good at memorizing exactly what's in the data, providing you sort of steer it right during training. And so remember from that picture we looked at earlier, we're feeding RPM, torque, speed, and into the wide part of this model, and we're doing it with a bucketized set of variables that we're crossing. Again, if you really, I'll give some references, or I do give some references on another part of the slide. You can sort of dig into the technical details of what's going on there. But the thing to remember is that the wide part of the model is sort of covering those relationships that we saw in that fuel map that we were looking at earlier. On the deep side of the model, that's the part that's going to cover generalizing or being good at generalizing when we see characteristics in the trips that we haven't seen before. And in particular, the make, the model of the year is an embedding that is driving that deep part of the model. And we also feed it many of the linear features that we saw in the feature list earlier.
How does your linear model do when you use those 6 features as opposed to the 2 features from the other model?
Better, yeah. And so in essence, where we would head if we followed that is we would just end up, getting the left-hand side of this more complex technique. For sure, the big hitters from a feature perspective are torque, RPM, and speed. And if I use those variables in a standard linear modeling technique, I get pretty close. I probably split the difference between what you're going to see this model's performance is and what the really cheap and dirty one was. So you're kind of in that continuum of where it's going. Yeah. Yes, so the reason that technique is being explored and actually exploited in this case is that clearly we saw from that earlier fuel map that there's a relationship between those variables. And so what I want to do is I want to create a sparse representation, a vector of each one of those things and cross them, meaning showing the relationships of where those sparse vectors are changing or clustering together. And that's what the bucketizing and the crossing does. By the way, I also feed the original continuous values to the model as well. So those crosses are not the only thing. I'm not throwing all the other data away. I'm just providing some manufactured or some engineered features to the model in addition to those continuous variables that we were looking at before. And the whole thing that's driving it is trying to explore that relationship between the variables that wouldn't be represented if I just fed the model every variable in particular.
And you essentially have one model which has the numerical predictors only, and the other one has the cross curves for the numerical predictors and the various categories like the positive and the one is trying to treat all the prompts as being the same and only giving RPM for the speed, and the other one is trying to sort of fit separate models.
That's right, yeah, exactly. I'll go through this really quickly. Here's some references at the bottom if you want to dive into the details, but how do I build this thing that I was just talking about? So we're using this wide and deep linear regressor that's part of the TensorFlow library. TensorFlow essentially wants me to represent or build this. One alternative that I have for building it is in a Python module that I'm going to submit. You'll see here that we're using Google's Cloud ML service to essentially train, do hyperparameter exploration, and then ultimately serve the models. And so it's dictating, or it's asking me to put together this representation within a specific Python module. And Google's TensorFlow library essentially sets up an experiment, essentially all the different training runs that I'm going to use to get to the ultimate model we're going to deploy. There's an estimator class, which this wide and linear model is a member of that estimator class. And we just went through the wide and deep features, and in particular the optimizer, Adigrad optimizer is what we're going to use. So we're specifying all these things within our Python module that we're putting together to represent the model in the way that we want it. And then there's 3 particular functions that we have to write to serve the data from a training, validation, and serving perspective. So as we grab features that we talked about earlier as being fed to the model, these functions are essentially mapping those features to tensors within the TensorFlow library that can effectively be used with their representation of these models. So really the only takeaway from this slide is it's Python that we're putting together. It's a module in the sense that, you know, it's like a Python library that you're building, and embedded within that library are all the choices that we talked about coming up to this point. Structure of the model, the features that we're going to use to drive it, and how to put all that together. Yeah, I think within Strata, when I submit my slides, they'll end up, you know, within the grand scheme of all the things that you saw this week. And so once we have this Python module, this is how the Cloud ML training jobs sort of represent, or how you put this together. So we stage data. Remember, we built with our pipeline the training and validation and test sets, and those get staged in buckets within the Google Cloud. We also have our code, which is this Python module that also gets staged in the Google Cloud. And then we have the definition of jobs that we're going to use to train the model and optimize it. You're going to see in a second a picture of how that optimization looks. They have a tool also that's called TensorBoard, very effective at looking at the internals of these models as they're being built. And so you can see things like loss function performance, look at all the different weights within the networks and watch how they're converging, and look at embedding spaces and how those have formed, in particular our case, the make, model, and year, and that sort of thing. And so that tool is very valuable. And then ultimately, when you get to the point where you're happy with the performance because you're scrutinizing it within this environment and looking at it within TensorBoard, you can cut a versioned baseline of the model and put that into their service as a specific model that's being served. And they provide Python bindings, among others, Java, other languages that you can use, where you can do inference with the trained model. In our case, the digital twin can make predictions about gallons per minute fuel economy using that hosted model. And so this schematic just sort of shows you how all the code and the data is being put together in the cloud and how it's flowing into a model that ultimately gets served and deployed. This is a picture out of TensorBoard. And essentially what we're looking at here is the convergence of the model that we're going to look at the performance of this model in the next slides. And so essentially the orange line dips down. You see the model quickly gain fairly good error performance. And then we see the evaluation set and the turquoise line come down and meet the loss of the training set. And essentially what we have at this point is the model, its evaluation set and its training set have converged to a low level of loss. And we can sort of stop the training and deploy a model and let it see the test data for the first time and see how well it generalizes. And that's what we'll see next. One thing to point out in this funny graph that I included with it, essentially when you first start training the model and iterating it, your bias is going to go way down. You're going to zoom towards the bullseye of the target for your prediction. But then if you over-iterate it, you end up over-fitting the model, and then you see the turquoise line sort of bend away from this. So if we did a poor job of this, we would essentially, our valuation performance would start to go to heck, and it would diverge. And that would be a signal that we've sort of overfit during training. But in this particular case, they're nicely locked together, so we're sort of in a position where we can step forward and look at the performance on the training set. So similar kind of picture. So we're looking at the distribution of error, this wide and deep model. And you can see that this one still has a tiny little bit of bias in it, but not as much as the cheap and dirty linear model. We're predicting a little bit low from a bias perspective on this one. So day in and day out, this is thinking that the trucks should be using a little less fuel than they actually are. And then the distribution is much tighter. In fact, what we'll do is we'll step forward and get a good comparison. So the orange was the baseline linear model, and the blue is the new wide and deep model. So you can see, yeah, if I want predictions about fuel economy in my digital twin, the blue wide and deep model is giving me a lot tighter error characteristic, meaning when it does make mistakes, they're not as far off the mark, they're not as far away from the bullseye. and in general, they're much smaller. And so we have a factor of almost 4 here of 3 and some change kind of improvement in the model. So now let's talk about the deployment process. I'll try to speed up here because how are we doing on time so far? Okay, a little, all right, I'll go quickly. So the deployment process now is what we graduate to. So we've got a model that we like, and we're gonna put that into production. So I will show you what this looks like. So there's 2 things that we have to do when the model is deployed. We're then, every time a trip is run with a truck, we're comparing its actual fuel use to its predicted fuel use coming from the digital twin. Here's the thing that we have to guard against. This is what we need to monitor in an online perspective. If the current trips and the features that we're capturing from those trips have drifted, changed in some way from what we originally trained the model on, we're gonna start to see degradation in performance. The distribution of that error is gonna change. And so when that model is deployed, there's a monitoring process that we'll have in place that's constantly watching the predictions that are occurring within the model and comparing that to the error characteristic of those predictions from when we previously trained it. And this is critical because as things drift in the world, you need to alert on that, and it's a strong signal that you need to retrain your model. Exactly how much drift you're willing to tolerate is somewhat a subjective choice. It really depends on what you're doing with the model and how much error you can choose to tolerate. So that's one thing you have to do when you've got the model deployed. The other thing is you're not gonna stop, right? This is an iterative process. You have a model in production, it may be of a certain quality, certain accuracy, and then you're gonna want to basically work on the next model, a better model. Perhaps you're gonna change the structure, you're gonna add new features, but ultimately you're gonna end up with a new model, and the first question you're gonna have is it better than the model that I currently have? And here's another spot where you have to do online testing, where you're gonna essentially say, I have 2 models, the one I'm currently using and the one I think I might wanna use. I'm gonna take samples from the current trip data that's occurring out in the world, and I'm gonna say, do I truly get better performance from the candidate model than what I'm currently using? And if the answer is no, there's really no need to go forward. You gotta go back to the drawing board while that production model keeps running, and you sort of look for the next best thing. And it's important to do this because unless it performs well on the data that's running in the wild, it doesn't really mean that it's a better model. So I wanted to go back to this guy quickly because remember we started the conversation, this is the person that we're working for, this is what the digital twin is geared towards, answering these questions. So what do I do with these digital twins? So let's take this particular truck like the Peterbilt, 579 that's running here. Every single one of these blue dots on this timeline is a trip. And then the orange and the green line are the statistical boundaries, 2 sigma away from normal or 0 error performance. And we're essentially looking for this truck leaving the bounds of that statistical control. If it starts to use more fuel than it normally does, or I guess you could also, but this would be more rare, start to use quite a bit less fuel than it normally does, those are indications that something is wrong and that the fleet manager needs to dive into it. So this is the essence of how you would answer, are my trucks fuel efficient? We have a model that's tracking that fuel efficiency, and if on any given day there's an activity feed or an alert essentially that says, hey, this truck is starting to exhibit through a series of trips perhaps higher than normal fuel use. And so this is a way to build up asset performance monitoring with these digital twins around a physical asset like fuel use on a truck. The other thing is they wanted to ask is, and what wanted answers on is, do I have the best trucks for my operation? So you can do something like, say, in August of this past August, last month, I have 7,000 trips that I ran within my fleet and 500,000 miles, 170,000 tons of freight. If I had a Freightliner, what would the fuel economy have been? And if I had a Volvo, what would the fuel economy be? And so this is a very previously unanswerable question in essence, because it's really tied exactly into the trips that this specific fleet ran. and the model understanding of these specific make, models, and years of trucks. And so as it turned out, when you look at this specific use case for the month of August, when we started out and looked at the actual trips, because of the driver bias, the Volvo looked better than the Freightliner. But then we take the driver bias away, because we talked about that earlier, we have a special model that does that. We end up with trucks that look like they roughly have exactly the same fuel economy for the trips that they run. But they ran different trips. And so if we take the whole set of trips and use the digital twin to say, hey, if all the trips that the Volvo ran, the Freightliner also ran those, and vice versa, what would the fuel economy be? And it turns out that the Freightliner for this fleet under these conditions with these 7,000 trips had a 0.5 mile per gallon better fuel economy. It was moving more tons of freight per gallon of gas than the Volvo was. And so that's the kind of insight that can come out of a digital twin for these fleets. And it makes a big impact. If I had 500 trucks in my fleet and I had this kind of change in my fuel economy because I had the right truck for my operation, it's millions of dollars. And so, again, it harkens back to there's a lot of fuel flowing through these vehicles, so just little bits of insight about what's the right thing for the right job makes a big difference. I'm going to step through these quick because I know we're probably pushing up against our time. The real value that I want you to take away in a nutshell for the digital twins is kind of what we were getting at earlier when we talked about tire pressure. You said, hey, what about tire pressure? When you have a digital twin and it's dutifully sitting there, calculating the predicted fuel economy of your truck, you can introduce changes in your fleet at any given point in time and answer the question, what did that do? Is it good or is it bad? And if it's good, how much? And if it's bad, how much? And so really what you want to know about these from a value perspective is it puts you in a position to drive your decisions around visibility and knowing the quantified difference that you get. One second. And then, again, here's the technical aspects of the digital twin that I'd like you to take away. This is a model built with the features that we've captured around the trip that are driving fuel economy. It's using a traditional machine learning workflow, and in this case, we use TensorFlow and Python and Cloud ML at Google. And its value really is it sits there and tirelessly tracks the fuel economy of every truck every time it's used. So you can find the needle in the haystack. You can find that truck that's suddenly starting to consume more fuel than it should. And then here's the kicker, the real takeaway. Digital twins and this kind of digital transformation for industrial companies, fleets, it's really about having the right information to the right person at the right time so that they can change the outcome before it actually happens. Once you burn fuel, you can't unburn it. That's spent money. But if you provide this kind of insight to the fleet, they can, and to the right people within the fleet to make the decisions, they can stop the fuel from being burned before it's being burned and put the money back in their pocket. And that makes up a big deal. So, thanks, that's it. One question?
So when you're talking about like changing the tire pressure, for example,
yep.
Is that you tweak the model to represent that, or is it you physically change the truck and see if it does better than the model?
Yeah, so the only control that you really have to exert, you don't change the model. The model basically will expose the difference that happens because of the tire pressure change. And so,
so you do the experiment.
You do the experiment, and then you look at, and the way in which you're evaluating whether the hypothesis was either refuted or not is the same as all A/B testing kind of approaches. And then you have to look at whether the impact is significant and what your confidence is in that. Same old stuff from a statistics perspective, but now you have the basis around which to do that. Question? Yep. Yep.
But if the driver has that much impact, if you want to focus on training the drivers to like all do like rather than like
yeah, actually, you should work for Phenomics. You should come to Phenomics and work in Phenomics. So the model that we have that's tracking the driver performance, part of it runs in the vehicle itself and provides audible feedback to the driver to more effectively drive the trucks. So we have a product called True Fuel. that is a real-time driver coaching and analytics for drivers, specifically for that component that is driven by the fuel economy component that the drivers have an effect over. And so you're absolutely right. The only way to arrest that is to give them feedback in real time. And we do it somewhat unobtrusively with different tones having to do with different things they're doing that are wasting fuel. This particular model is sort of focused on the truck itself. And so we need to make sure we get a handle on that bias that the driver introduced. One modeling technique that we don't have in production, but we're looking at doing next, is we think we can probably train everything in aggregate. So if we have the drivers, we know who's driving the truck from a driver ID perspective, unique drivers. We think we can take them into an embedding space where we don't have to presuppose what the driver effect was and subtract that off. We just lump that right in with everything else, the make, model, and year of the truck and the driver ID, and come up with an embedding space for all those drivers. That embedding space ultimately should look like, hey, over here are the good drivers, the ones that aren't wasting very much fuel due to behaviors. Here's the really bad shifting drivers. Here's the really bad idling drivers. And so that embedding space should be able to separate out what all those effects are, so we don't have to precondition the pipeline with taking that off. We haven't done that yet. I think it's fertile ground. We're probably going to look at that soon.
Probably extend this question a little bit. So could there be a boundary so you cross that all of a sudden you kind of like judge on the driver and say you're a bad driver, you're not supposed to be working here, kind of like or maybe in another sense, I know these trucks are equipped with GPS, right? So they know how fast they drive at every location, and so maybe they optimize the road for you. Say you need to turn at this location, or you get off that road. Now all of a sudden, so the driver becomes kind of like a tool that to drive the car instead of like just it's working for you.
Yeah.
Right? So,
Yeah.
have you think about like this, like at which point? So far this topic has like heard today, so I really like it. So, but like.
Yeah, I mean, you bring up, I mean, with the conversation could go very, very deep. So everybody understands that they're trying to automate vehicles, and in particular commercial trucking, they're trying to automate it as well. And so when they automate it and there isn't a driver in the seat anymore, what would they do from an automation perspective to make sure it's the safest, most fuel efficient truck that they could automate? And you're basically pointing at what it is that they're gonna model and code to make it fuel efficient and safe. Personally, because I know we work with fleets every day, we don't want this to be punitive. I think people work better when you motivate them to be professional, and they actually are and do want to be professional. So we tend to give that feedback about what is it that you should do in such a way that they're scoring higher, or they're looking at like a batting average, right? Or some score that they get within a sport. So they're trying to achieve a higher score. In a video game even, you could look at it that way, as opposed to, I'm gonna fire you if you don't achieve this result or whatever. So point being is you wanna make sure any of these modeling techniques that you're using are giving feedback to the right people at the right time, as we mentioned at the end. And as far as driving goes, that feedback is real time. I mean, when you're doing things that are either efficient or not efficient, you wanna give that at that moment. Thank you. Yeah. No, it's jargon. So digital twin actually is an old term. I think it even has its root almost back in the physics-based models. And so it's had a resurgence because also General Electric is using it quite extensively in their product line, locomotives, jet engines, things like that. And so it's a good way to get a strata talk by using the term digital twin. No, but you're right to point it out. It's just an effective way to quickly capture in a concept what you're doing. You're mirroring a physical asset. You have a twin for that physical asset to mirror its performance. But it's an old term. We're out of time. I'll stick around so I can answer other questions. Thanks everybody for